Okay, so let's get today's lecture started. I'm very sorry for the 5-minute delay that happened. So today is 24th August, 2023. Let me, now that we have done the initial part of the magnetization and how does that evolve as a function of time. Now the next series of steps that we saw were, what is chemical shift? I said that the chemical shift arises because of the fact that you have differing electron clouds. For instance, the B field that's experienced depends for every given nuclei, depends upon the shielding parameter. And I also said this shielding parameter, what you measure in solution state is an isotropic shielding parameter, which is nothing but the trace divided by 3, indicating that you get only one scalar value for a 3-dimensional effect that is present in the system. We also defined something like offset, which initially was as omega naught minus omega RF. But as you are able to realize, for every given spin, since there will be a shielding parameter, the offset will now get defined by where is it resonating, depending upon its shielding. Okay, with that being said, the parameter that people generally use in NMR is called chemical shift. For an ith nucleus, it actually gets defined by capital omega I minus omega ref, the whole divided by omega naught times 10 power 6. So what is done here is that even for a standard reference, so what is ref here? Let me write it. This is the standard reference with respect to which we determine this parameter called chemical shift. Generally, this reference is an internal standard. For instance, tetramethyl silane, also called TMS for short, is used within an NMR sample in order to get the offset with respect to the reference. Remember that within this, you have an RF pulse whose transmitter frequency is reference. In theory, you don't have to complicate it this much. You could have also written the same equation as is also equal to omega I minus omega reference. I didn't write it this way because the omega RF and omega REF might confuse you guys. So therefore, I didn't write it. So please be careful. These two are different things. Okay, so this and that are one and the same because you're going to have omega RF in both of these. So that will get cancelled from this part and this part. And you have omega I minus omega ref divided by omega naught times 10 power 6. And what is this omega naught here? The omega naught is the Larmor precession frequency at field B naught. Okay, now let's try to understand what are the units for this. This is given in units called ppm, which is parts per million. Similar to the fact that the magnetic field gets defined in megahertz, while conventionally it's done in Tesla. Similarly, one should not get confused that ppm is a concentration unit. How can energy be expressed? So what we are trying to do here is to have a definition of chemical shift that is independent of precession, the Larmor precession frequency. Why this is to be done, I'll tell in a moment. But before going there, let's understand what is million about this whole thing. What is parts per million? Why does the parts per million come? It comes up because of this factor that we end up multiplying the entire omega I minus omega RF by omega naught. This happens largely because you're able to realize this precession frequency will be in megahertz, so will be omega ref. Or you can go here where the difference in omega I and omega ref will be in kilohertz, or even actually a few hertz, divided by something in megahertz. So what is going to happen here? You're going to have a small number divided by a number that has 10 power 6 on top of it. So this is going to be trouble where you're going to get numbers that are really small. So due to which 10 power 6 is multiplied, which is where the million starts to come. That's an important aspect that we should keep in mind when we are doing this, is that the delta, sorry, I got a little distracted. Um, yeah, I forget what I wanted to say, but anyway, so the whole idea here is that the 10 power 6 million comes because of the fact that you have something in the denominator that is huge. The reason why why delta is defined in ppm is because the omega naught is in the denominator. Therefore, you want a parameter which is delta that is independent of the B naught field that is applied. This is an extremely important thing to understand, because as we start going, we will realize that in the chemical shift frame, irrespective of taking the spectrum of methanol in 100 megahertz, 400 megahertz, or 800, or any spectrometer field strength, you will literally measure the same set of chemical shifts for the nuclei that are involved. I hope this makes sense. Let me repeat again. Slowly, we will realize that since the Larmor precision frequency is dependent upon the B naught that is applied, the energy differences, therefore, which generally is what is spectroscopy, right? What do we say as spectrum? We call a spectrum as one where you end up plotting intensity as a function of energy. Just as an example, let's say we take a spectrum at 100 megahertz. Remember, the energy difference is going to be very close to 100 megahertz, depending upon the small changes in shielding that come. When you go 400 megahertz, the energy difference for the same system is going to be 400 megahertz, and it keeps changing. Due to which, what is going to happen if whatever spectrum that you get and whatever spectrum you get in 400 versus 100 megahertz, it's going to be quite different, which we do not want. So therefore, what is being done is that if the spectrometer field strength is divided in the denominator, you get a bunch of chemical shifts for a molecule that's independent of the field of the external static magnet that is being present. So therefore, this chemical shift is an important parameter, and irrespective of which country you measure it in, which field strength you measure it in, we now have one variable or a bunch of variables for a given molecule that can be compared across spectrometer field strength. So this is the whole reason why chemical shift is defined with respect to omega naught. The reason that million comes is that you have two small numbers divided by a million number. So therefore, you want to have a 10 power 6 in order to make sure numbers are discernible. Now, what I'm going to do is to show you guys a few examples of the same. Previously, we have just taken some tentative numbers um, for ethanol. But now what I'm going to do is literally show you those for some molecules. So this is a wonderful web page. So if you end up going to organic chemistry data.org slash this website that I'm showing right now, you have a nice page where one would end up seeing some bit of NMR theory, which we have already discussed, where they try to say versus precision, how does a spectrometer look, and all that. But the major reason what I would like to look here is chemical shifts. So this is something we have seen before. They're trying to give an idea if there's a spin that is being present, how does the effective magnetic field change right around it in order to get a slightly different chemical shift depending upon where it stays. So if you're able to see, this is the chemical shift range that's defined in ppm for a proton. One could have a minus 10 ppm that comes for a ruthenium complex where the proton is directly attached to the ruthenium metal. On the other hand, the calculated chemical shift of a naked proton, if one could isolate it, appears somewhere around here. Interestingly, I think the example that they are trying to show is that a proton that's attached to a O plus ends up coming somewhere around 18 ppm. In my experience, I have seen the maximum around 16 ppm or so for I motive samples, but of course, there might be some examples in literature that go even more downfield. So from here on, we'll be using some terms called downfield and upfield, which I just did. Any proton that appears downfield and upfield are all relative parameters, where let's say if there is a proton here that appears at say 8 ppm, anything that's lower than 8 ppm is upfield, anything that's higher than 8 ppm is downfield. One important aspect all you guys should take care is that the chemical shift almost always runs lowest on the right side to the highest on the left side. This is kind of counter to what generally is done in spectroscopy, where you go from lowest to highest in value. So be careful about it. But anyway, we are not worrying about what is the exact free energy difference. All we care about is the relative energy difference between the spin that you want to see with respect to a reference, for instance, tetramethylselene, divided by the spectrometer field strength. So therefore, you get delta values for different systems. So here is where the standard is given. And this helps in certain way where you can compare spectra across different fields. So these are some excellent examples to start with. I'm not going to go into details. You will not be tested on any of these chemical shift values. I'm doing this lecture just to impress upon you guys that if you end up changing a little bit of the chemical nature of the atoms bonded to the proton, how sensitive the chemical shifts are. So if you take a look at this, all are organic molecules. In every aspect that you're seeing here is a CH bond that is being present. All of them are CH single bonds that are being present. And they're trying to give you an idea as you end up changing the way the moiety looks, how does the chemical shift ends up changing? So for something like a cyclopropane that's present, the proton ranges between here to here, depending upon some substituents. But as you start increasing the complexity, more importantly, as you go more and more electronegative in terms of the atom that's bonded to the proton, the chemical shift starts to go more downfield. So the classic example of the same, for instance, take this one where you have an CH, which is next to a carbonyl or a C double bond N or a C double bond C. It comes somewhere between, say, 1.5 to 2.5 ppm. The moment you go to a alkane directly bonded proton, ends up coming in the range of 5 to 7 ppm. And even further, if you have an aromatic system, for organic molecules, it comes somewhere between 6.5 to 8.5 ppm. And when it comes to the aldehyde, it ends up coming between 9 to 10 ppm. We are not extremely concerned about why are these values coming up. I'm just trying to highlight the fact that these yet again indicate the importance of chemical shift, as one would be able to measure it for different aldehydes, different groups that are being present in terms of the alkyl group attached to the aldehyde, to understand how these chemical shifts are influenced and therefore characterize the molecule. This is an excellent example where different atoms, when bonded to a methyl group, where does a methyl group chemical shift come? As you're able to see, it can span from something like -2 ppm to +4 ppm, where -2 comes up for a directly bonded lithium to the methyl Me minus maybe Li plus. In such a kind of situation, you get something around -2 ppm. On the other hand, when you have a CH3F, it comes around 4.2 ppm, yet again indicating if you end up plotting the electronegativity of these atoms to the chemical shift, they will have a very nice, reasonably linear correlation that starts to come up. Okay, I hope these examples have been useful to understand how a proton chemical shift gets influenced by the atom that it is attached with. Let's take this example. I think it's a wonderful example to see. They are talking about how the calculation works for these systems, which I'm not going to be concerned about in this course. Chemical shifts can be calculated using DFT techniques, which we won't be covering in this part of the course. So this is an example of a CH standard where the proton ends up appearing at 1.55 ppm. The moment you have 3 methyl groups that are appended to it, you realize that the chemical shift actually interestingly changes a little more downfield. I'll leave you guys to think why that's happening. The moment you start to put it in a bridged hydrocarbon that's being present, I forget what it's called, 221 norbornane or something, that kind of a system, the proton gets even more downfield shifted. Yet again, you are able to see all are literally CH alkanes with no complications or no electronegative groups being present. The moment you start to have different groups that are there, the chemical shift clearly indicates a different, suggesting differences in the electronic environment that it is exposed to. Look at this extremely interesting ring where there are 2 protons that are present. both are literally CH protons, where the other three bonds are carbon that's constrained by a ring, you see that the chemical shifts are quite different between them. And a super cool example is the cubane molecule, where the proton resonates at 4 ppm. So it's always a fun activity for synthetic chemists to create such molecules to determine what is the chemical shift. And generally, these kind of studies help computational chemists come up with ideas in order to predict such chemical shifts as reliably as they could. This is something we just discussed a moment earlier. When you have CH3Li, it goes to -2 ppm. Tetramethylsilane, where the methyl group is attached to a silicon, you reference it at 0 ppm. Methane, when dissolved in a solvent, is measured at 0.2 ppm, meaning that it's very close to this. The difference comes up largely because that the carbon is now attached to a silicon versus a proton. That gives a small difference. Ethane, where two methyl groups are attached, goes downfield. Methyl iodide is at 2.2, methyl bromide is at 2.7, methyl chloride is at 3, and methyl fluoride is at 4.3. Nicely indicating how chemical shift indicates the changes in electronegativity that are being present. Now, there are examples of carbocations where aromaticity also matters here. So if you go take a look at some of these examples of how a carbanion, carbocation, how the resonance plays a role, you will understand how chemical shift ends up changing for each one of these cases. I'm sure in chemistry examples, you have seen several times where these kind of molecules come, and the way people end up characterizing it is using NMR spectroscopy. So this is a wonderful example where all of you guys would have studied how aromaticity plays a role. And there's an example of aniline, where you have ortho, meta, and para protons. There are three different kinds of chemically different protons. And the example that is nicely shown here, ortho and para slightly come upfield with respect to the meta. If you guys might recollect why this ends up working, you would realize that there is a resonance structure which increases the electron density around ortho and para, while it decreases it or does not increase it in the meta, which is what you are able to see here. Going with the same argument, OMe should also play a role, but oxygen has its own different properties when it comes to electronegativity, resulting in lesser difference between the chemical shift in the orthopara versus meta protons that are there. And methyl group, toluene, is even more subtler than OMe and does not have a lone pair and ends up increasing the electron density in ortho and para positions more due to the Baker-Nathan effect or the hyperconjugation effect, which is a much more subtler effect than resonance plus R effect itself, which means that the ortho, meta, and para are actually closer to one another. The example of nitrobenzene exemplifies things even more, where even the para starts to resolve itself from the meta peak, meta resonances that are there. The important thing to note here, I hope you guys are able to understand, the orthoproton sees only one set of metaprotons. Therefore, it starts to come up as a doublet. Okay, so if one is imagining ortho to be A, for instance, there are two A's being present because they are identical due to symmetry. And if you're looking at the next system, so that is present, you have, let's say, I'll call it P just for the heck of it, or M. So, and M has one proton and one proton. Remember, there are two protons. By solving the AMX system, I hope you guys remember what I did in the other day. If you have an AMX type system, so metaproton is coupled with ortho and para. In reality, if the scalar coupling magnitudes are different, you're going to get a doublet of a doublet. But I was telling you an example where if these two end up matching with each other, you will end up seeing a triplet. And this is a nice example of the same, where I'll zoom in to show you where the metaproton ends up coming as a triplet. If you zoom in further, you'll start to see some small deviations that come. But for all practical purposes, let's assume that it's a triplet. Maybe there is a few other interactions that come due to several bonds. There's something called a para effect that is there. I'm not going to go into the details. And similarly, for the para proton, there are two metaprotons being there, which comes up as a triplet, right? Almost always, whenever you acquire scalar coupling, a triplet should be 1:2:1, and a doublet should be a 1:1. Interestingly, you will also see that the intensities start to change a little bit, where they are not exactly 1:1 or 1:2:1. These are effects that come due to the smaller differences in chemical shift and scalar coupling, which I won't be able to go into the lecture due to the want of time. Well, this is an important lecture for people to understand the numbers that we get out of NMR are super crucial. So this is an example where if you have a lone pair of electrons that are being present and that's anti to a given proton versus lone pair that is not anti, in some ways gauche or something like that, makes a huge difference in terms of how the interaction of the lone pair happens with the proton, due to which chemical shifts start to be quite different. So this is one nice example. If you're having the proton in the equatorial position with lone pairs being anti, what is the chemical shift versus the lone pair being a little bit gauche, you end up seeing a different chemical shift. And few other examples where you have a competition between anti and syn kind of a situation where the chemical shift starts to come. I think this example is much well shown for cyclohexane systems. Yeah, the aromatic systems is a lot more fun. Well, let's see the cyclohexane type system. Yeah, this one. So these are steric factors that come into play. I'll probably stop doing this soon because I expect you guys to go back and read what is written here. It's a lot more fun than whatever I'm speaking. So this is an example where you have two equatorial protons that's being present with a given functional group that are there. In order to give you an understanding that a steric group plays a role, they only change this proton to a methyl group, and they're able to show that the chemical shift changes uh, substantially. Anything about 0.02 ppm change in proton is significant, and here you see a 0.2 ppm, indicating that there is a serious effect that comes due to this methyl group, which is what is discussed as the steric effect that's present. Similar is the example where you have toluene, where the proton is at 7.1 ppm, but if you end up substituting every proton in toluene to a methyl group, the ortho position proton ends up changing to 7.27 ppm. Potentially, the meta and para also change, but their changes might be lesser because the steric effect is more pronounced on the ortho position than the meta positions, right? And take for an example, something like this is very interesting for me. You just have one extra pi electron above this proton that changes its chemical shift significantly, and that's the only thing that's being absent. And one is able to distinguish the methylene proton. You might remember the example that I gave earlier on, where these are characterized as diastereotopic proton. There are multiple chiral centers here. Each one of them is a different chiral center. And significantly, the chirality is broken due to the double bond. If there were a double bond here, then it would have probably remained chiral, but the pucker would have been different. So, but interestingly, you're able to realize how the proton is able to get influenced by the groups that are being present. This proton, which has other groups, ends up going as much as 2.7 ppm, but the proton, which just has a double bond, doesn't change much. And interestingly, these two might look very similar to you, but even then, the chemical shift is super sensitive to who are all nearby. With this, I hope I have driven the point to you that chemical shift is a super important parameter and will give you structural information, not just chemical moiety, but also structural information on what's going on. And significantly, these are influenced by the electronic effects that are being present and experienced by the nuclei. Okay, moving on, similar to this, there are also scalar coupling differences that start to come. I hope you guys are able to realize that scalar coupling gives you an information of the neighbors that are present, more on the number of neighbors that are being present. A common rule of thumb is that when you have n number of spins with, say, quantum number I, then the multiplicity will go with as 2ni plus 1. Meaning that, let's take an example. This is the problem that was given to you in your quiz. Let's say this is a situation you're looking at what will be the multiplicity of this proton with respect to two identical protons that are being present. So how would one end up calculating it? It will be more like for this proton, 2 times n is 2, where n is the number of protons that are present that couples with them. And then I for protons that is being looked at as half, and therefore you're going to get 2 plus 1 a 3, which means that this is going to be a triplet. Similarly, for these protons that are being present, these two are identical, and it ends up coupling with a single proton. So it's going to be 2 times 1 times half plus 1, which is going to be 2, which means these are going to be a doublet. Okay, so the 2ni plus 1 nicely works out, but be very careful that I is calculated for chemically equivalent protons. All right, so let me complicate life a little bit and ask you, if you have a situation like say CH, CD, CHH, for instance. Okay, and let's ask ourselves, what if I want to find the multiplicity of the CH proton here? So what is going to happen? It depends upon the 3JHH coupling and the 3JHD coupling, the magnitudes of these. And just for the sake of simplicity, let's assume that this is 10 hertz, and let's say this is 2 hertz. So what is going to happen here is that since 2 are being present, these 2 protons will split this proton into a triplet. So first you're going to get a triplet, and due to the CD coupling, so this is due to 3JHH, and since you have 3JHD that's present, what is going to happen? The triplet will get further split into something. We'll see what that something is, okay? Largely because 2n is 1, I for deuterium is 1. So you're going to get 2 plus 1, which is a triplet. Remember, this triplet is not going to be 1:2:1. It's going to be a 1:1:1. Why is it a 1:1:1? You have the 3 states that are being present, 1, 0, and -1, which are almost equally populated, due to which you are going to get a 1:1:1 triplet for this kind of a case. Okay, so therefore, how will the spectrum look right now for this kind of a case? You're going to have, okay, so what does this give you is that if you're able to get the hyperfine splitting, okay, let me also write some values here. So this will be like 2 hertz, 2 hertz. The middle of this to middle of this will be 10 hertz. Middle of this to middle of this will be 10 hertz. So the hyperfine coupling provides you an information about how the neighbors are. And that's extremely critical. And the advantage of this is that the scalar coupling magnitudes will also be similar for one another. Okay, so let me take yet another example to show what's going on. So this is an example. So if you go take a look at it, this is a simple AX system that we solved. I hope you guys remember, for an AX system, A comes up as a doublet, J comes up as a doublet. That's the example we are seeing here. Here, they're just trying to show the magnitudes of scalar coupling for multiple bonds, and that to heteronuclear scalar couplings. So let me actually not do heteronuclear. Let's just do proton. Maybe it'll come a little later. Went already to aromatics. Yeah, some first order coupling rules. Yeah, this is an important thing to remember. The 2ni plus 1 translate itself to something called, translates something to itself called a Pascal's triangle. So what's a Pascal's triangle? You can build up this 2ni plus 1 as, when you have no coupling partners, you get a singlet. When you have two coupling, or rather, as one coupling partner, it comes up as a doublet. And when you have 3, it comes up as a 1:2:1, which is a triplet. We are talking about I equal to spin half partners. And if you have 3 of them, you're going to get a 1:3:3:1 quartet, 1:4:6:4:1 quintet, and so on. But remember, it is assuming that the J values are constant for them, and therefore this kind of splitting starts to happen. So that's the example that's being shown here, where the scalar coupling starts to increase, or increase the number of resonances that are being present right about the chemical shift. And depending upon the magnitude and the number that are present, you will get extremely hyperfine spectrum. For instance, this is an example of a doublet of a doublet. Don't ask why the intensities are not same. That's for some other discussion. And this, the example in the middle is a doublet of a doublet of a doublet, where one set of chemical, the scalar coupling matches, giving a triplet kind of, oops, I'm sorry, triplet kind of picture. And as you start increasing the complexity of the spin systems that are being present, then you see that the same resonance starts to split into many different multiplets. So I request you guys to go back and take a look at this. These are examples of how, if you have something like a couple to 4 protons with very different scalar coupling values, how will be the splitting that comes up? It won't be a simple quintet, but it's going to be called a multiplet. Okay. The request here yet again is that you guys go back and take a look and read a little bit of this to understand and appreciate how, when you get such a complicated spectrum for a given proton, NMR gives you a lot more idea on what's going on. So I'm just going to paste it here. So if you're able to realize it's a bunch of 4 protons that are coupled, and it's giving you an idea how the spectrum, how complicated the spectrum looks with different intensities. These are all simulated, but if one ends up carefully sitting and deconvoluting what is being present, one will be able to understand why these kind of couplings start to appear. Yet again, indicating how powerful the technique of NMR is and the parameters that one ends up getting. Yeah, so go back, there are some practice sets that are being present, which should help you understand what goes on. Unfortunately, I will not be testing you about this in this course, so do not worry much about it. But yet again, gives you an idea how powerful scalar coupling and chemical shifts are. So there is one person who asked, how do these values change? So this is one example of it, where you're talking about a 2-bond scalar coupling. All these cases are 2JHH scalar couplings that you're trying to look at. You're able to understand and appreciate, depending upon the moiety that is being present, these values change drastically. For instance, something like this literally have no coupling between them. That's not surprising, because although these might end up being diastereotropic for a given pucker of this 5-membered ring, as a function of time, the puckers end up sampling every possible conformation, resulting in averaging out of such scalar couplings to almost zero. And slowly you're also able to appreciate that the scalar couplings could be positive or negative, depending upon the overall orientation between them, right? And the functional groups and the effect that they end up imparting on the electronic environment also ends up influencing this. Go back and take a look at this resource. You have many examples of what's going on. Okay, umpteen number of examples to understand how the couplings are rather different. Yeah, the 2-bond J couplings, each one of them has a reference on how it's being measured. Most often we won't be worrying much about it. We'll be looking at something called vicinal couplings, where 3-bond J couplings are the most commonly looked at. And as Jeet nicely pointed out a few weeks back, these scalar couplings are indeed related to the dihedral angle. So the moment you are able to measure a certain dihedral angle, measure a certain scalar coupling, one would be able to associate it with a certain dihedral angle. Slowly you're able to realize NMR not just gives you the qualitative picture of how chemical shift changes, scalar coupling changes, and the magnitudes of scalar coupling, gives you an idea of conformations and chemical structure, but slowly one can actually incorporate it to get higher order structures. For instance, a scalar coupling could be used to get the ring pucker. So let's take a look at this example. There you go. So I hope this is visible. And the example that we are trying to see here is that what is the coupling between H1, HC, and HT? And I think that's a methyl group that's being present, something like that. They're trying to give you an idea as the dihedral angle changes, how does the scalar coupling, so it's an axial proton that they're trying to look for, how does the scalar coupling changes? You're able to see that it changes to a magnitude of about 10 hertz as it encompasses different dihedral angles, right? So if you're able to see, the H1 to HC versus HT will change quite a bit. Of course, at some point HC becomes HT, and therefore they will have their own match that is being present. right? And the example that's being given here is a 3-bond scalar coupling with respect to the angle theta, which is the dihedral angle. And these are constants that are empirically derived for different systems done by Karplus quite a while back. Okay, so I can go on forever showing you other examples of how scalar coupling gets affected by distance, the position, but that is when it gets a little too boring for people like Jeet, me, and Minish, because we accept it exists and we want to go ahead and use them towards structure determination of biomolecules. Okay, so also another nice section on long range J couplings. I did mention that something about 3 or 4 bonds becomes small, but you can see how small it becomes. There are still some examples where such very long range scalar coupling is also appreciable. So take an example like where you have a 4-bond scalar coupling between proton-proton of about 10 to 18 hertz. This is significantly high. This largely comes up because of the certain conformational preferences and the orientation of these protons, which causes such high values to be present. So there you go. Slowly, NMR spectrum starts to get super complicated, where some of the splittings. So this is one example where a triplet gets further split into a doublet, and the doublet is of magnitude of 1.6 hertz, indicating equatorial interactions. So if one is able to obtain a high resolution NMR, one could get a lot of details about the chemical structure that he or she is working with. And each one of the different things that we put up here causes changes in scalar coupling. So this is one example where a 5-bond scalar coupling between these two red protons sits at 11 hertz. It's hugely significant. Whether that is the longest scalar coupling that's measured, I do not know. Maybe literature has some other records of 6.7 bonds that I'm not aware of. But as I said, that's not the focus of the course. The focus of the course is to give you an idea of how NMR spectra can be predicted from where you start with and why does NMR come up and what can we learn from it. With that being the case, I would like to leave you guys with a couple of questions, which I expect you guys to solve for the next class. We'll start the next class trying to discuss this question. The question is this. Currently, do not ask why we are using deuterium, but quite commonly, we use CDCl3, which is deuterated chloroform. As a solvent in NMR measurements. What I would like you guys to tell me in the 13C one-dimensional NMR spectrum, what will be the multiplicity for carbon-13? This is one question. Okay. Similarly, if you have answered this, I request you to go think about when you have DMSO D6. What is DMSO D6? Dimethyl sulfoxide, but instead of having proton, all of them are switched to deuterium. What I request you guys to do is to find in proton NMR, when you end up taking DMSO D6 solvent, it gives a peak around 2.5 ppm. I want you to find what is its multiplicity, why does it arise. Basically, I want an explanation based on whatever we did today. What is the multiplicity? Why does it arise? And this is for the proton NMR. And I want you to do the same thing for carbon-13 NMR. What is the multiplicity for this carbon? Remember, when you're taking a natural isotopic abundance, there is C12 99% and there is C13 1%. I'm talking about keeping the same 1% with this given moiety, what all you end up seeing. I will try to show you in the next lecture how does a spectrum, carbon 1D spectrum for these two solvents look. And then we can start there by appreciating, okay, we are slowly starting to learn how to predict chemical shifts and scalar couplings that are being present. Good. So this was a very easy lecture in comparison to the other lectures we have had. Just to exemplify the fact that whatever we end up measuring is an important parameter. And when we measure it, how can we end up using it? As I've repeatedly said, this course is not about learning how to use it as much, but to ask, how does it arise? How can we measure it?